Hi, happy people. This is Mr. Wilcox coming to you from my kitchen table. Last week we were talking about series and sequences. We introduced ourselves to that. So we're going to finish off the year with some trigonometry stuff. So today we're going to learn how to reduce radicals. We have done this lesson before in class. I just want to review it before we talk again about fractions that have radicals in them because we will use that a lot with trigonometry. So if you don't know the first 12 perfect squares, uh, go ahead and write this down. I'm going to pause so you can write it all down in your notebook. And when you're ready, hit play again. So these are the first 12 perfect squares, and the reason we want those is because we also know that the square root of 1 is 1, square root of 4 is 2, square root of 9 is 3, and so on. So we're going to be looking for numbers that are perfect squares so that we can reduce our radicals today. So just a reminder what a radical is. I'm going to pause here so you can write this in your notebook. And when you're ready, hit play again. So just a reminder of radicals, what we call the square root symbol. We've dealt with radicals that have indexes, so that are the cubed roots and fourth roots and fifth roots and sixth roots. And the number underneath is called the radicand. So in the square root of 2, we could call that radical 2 as well because it's a radical, and our radicand is 2. And when we multiply two radicals, we multiply the radicand. So the square root of 3 times the square root of 5, square root of 15. A radical 3 times radical 5 is radical 15. So here's what we're going to be doing today to reduce radicals. So again, I'm going to pause here so you can pause the video and write in your notebook and hit play when you are ready. So we use that multiplication rule in reverse to reduce radicals, and what we're going to try to do is we're going to try to multiply using those perfect squares. So for example, the square root of 20, the biggest perfect square that goes into 20 is 4. So if we change that to the multiplication square root of 4 times square root of 5, square root of 4 we know is 2, so that is 2 square roots of 5. So 2 square roots of 5 is the simplified version of the square root of 20. So we're going to do some examples. So the square root of 50, square root of 24, and the square root of 63, we're all going to simplify. So square root of 50, what are two numbers that multiply to get 50? Well, the biggest perfect square that goes into 50 that I can think of is 25. So if we change the square root of 50 to the square root of 25 times the square root of 2, the square root of 25 is a perfect square, so that's 5. So that gets us 5 square roots of 2. Square root of 24. There are a lot of numbers that multiply to get 24. We could use 2 and 12, but neither of those are perfect squares. We could use 3 and 8, but neither of those numbers are perfect squares. So the biggest perfect square that goes into 24 is 4. And so what number times 4 equals 24? And that's 6. So I'm going to rewrite the square root of 24 as a square root of 4 times the square root of 6, which gets us 2 square root of 6. There are no more perfect squares that go into 6. It's just 3 times 2. So we are as simple as we can get it. So that is 2 square roots of 6. All right, last example on this slide. If we have the square root of 63, there are, again, lots of ways we could multiply to get 63. 3 times 21 gets 63, but neither of those numbers are perfect squares. And so I'm going to use the square root of 9, because that is a perfect square, times the square root of 7. And so if I reduce that, I get 3 square roots of 7. 7 is not divisible by any more perfect squares because it is a prime number. So 3 square roots of 7 are as simple as it gets. All right. So you want to find the multiplication of two numbers. One of them needs to be a perfect square. If they're not perfect square, you can't simplify, so there's no reason to do it. So for example, we use 25, 4, and 9 here. Make sure you are using one perfect square so that it actually reduces. All right, with radicals, we will be simplifying fractions that have radicals. And so I'm going to pause here for a second so you can write this all in your notebook, and then I'll explain it, and then we'll do a couple examples and we will be done. So if we have radicals in fractions, the big rule is you cannot have a radical at the bottom of a fraction. So to get rid of a radical in the denominator, what we're going to do is we're going to multiply by that radical on both top and bottom. So remember, we can multiply any number by that magical number 1. And so if we multiply by the same thing on top and bottom, we are multiplying by 1. So if I have 3 over the square root of 2, if I multiply by the square root of 2 on top and by the square root of 2 on bottom, I am still multiplying by the number 1, so I'm not changing anything. So for my numerator, I'm going to get 3 square roots of 2. And anytime I take the square root of the same thing times itself, I'm essentially squaring it. So I should get that radicand out. So for example, the square root of 2 times the square root of 2 is 2. If you need proof of that, if I take the square root of 2 times the square root of 2, I get the square root of 4, and the square root of 4 is 2. And I can't simplify 3 square roots of 2 over 2 anymore, so this would be our simplified version of 3 over the square root of 2 is 3 square roots of 2 over 2. All right, a couple more examples that have radicals on the bottom. So if I have 25 over the square root of 5, again, I don't want that square root of 5 on the bottom, so I'm going to multiply by the square root of 5 on the bottom and the square root of 5 on top. And if I do that, my numerator will be 25 square roots of 5. Oops, there we go. And on bottom, the square root of 5 times the square root of 5 will get me 5. Now I can simplify 25 over 5, and 25 over 5 simplifies to 5. And I still have square roots of 5. Now what you can't do is you can't say, well, I have a 5 as a radicand and 5 on the bottom and simplify that. This radical is like a little protection barrier. You can't simplify anything in a radical by anything outside a radical. So I could simplify 25 divided by 5, but what I can't do is take the square root of 5 and divide it by 5 and call it the square root of 1. So 5 square roots of 5 is what this reduces down to, all right? So be very careful not to simplify anything inside a radical by anything outside a radical. All right, second example, we have 5 square root of 7 over the square root of 2. I can't have the square root of 2 on bottom, so I'm going to multiply by the square root of 2 on both top and bottom. And if I do that, I'm going to get 5. And square root of 7 times the square root of 2 is the square root of 14. And then on bottom, I have square root of 2 times square root of 2, which is 2. Square root of 14, we just have to double check that it's not divisible by any perfect squares. So it's not divisible by 4. 14 is not divisible by 9. And then we get to 16, which is already bigger than 14. So 5 square roots of 14 over 2 is as simple as it gets, because again, we can't simplify 5 over 2, and you cannot take the 14 and divide it by 2 because 14 is under a radical and 2 is not. So this is our simplified answer. Right? So that's how we're going to simplify radicals when we're using trigonometry. So we went through and we simplified some just radicals by turning them into multiplication, and we went through and we got radicals out of the bottom of fractions, so we can't have a radical denominator. So we learned how to change that. So I hope you are all happy. I hope you're all healthy. And I hope you all have a great